Welcome back to the Info Engineer. Today we're tearing straight into an explainer on what is, hands down, the most dangerous phase of project budgeting. I'm talking about earthwork estimation. Before a single excavator even gets unloaded on site, the financial reality of a multi-million-dollar project can be completely derailed. So we're going to take a highly analytical, practical, and definitely cautionary look at the hidden risks of moving dirt. Because, well, as we're going to see, the ground beneath our feet is way less stable and far more expensive than it ever looks on a 2D grading plan.
So here's our game plan for today. First, we'll hit the earthwork budget danger and look at exactly why this phase destroys margins. Second, we'll get into the science of why soil simply isn't a constant. Third, we're going to break down the grid versus cross-section analytical methods. And finally, we'll run through a pretty crucial checklist for avoiding common estimation mistakes. Let's get into it.
All right, part one, the earthwork budget danger.
Okay, let's talk about risk. Why is earthwork notoriously dangerous for a budget? It really comes down to the core structure of the contracts. Earthwork is almost always bid on a lump sum or firm quote basis. What does that mean for you? It means the contractor is shouldering an incredibly high degree of financial risk. If your initial measurements or volume estimations are off by even a tiny fraction of a percent, the client isn't writing a check for the difference. The contractor just eats the loss. It's brutal. You combine those notoriously narrow profit margins with sky-high operating costs, and you've got a highly volatile situation. Underestimate the material you need to cut, haul, or fill, and your profit margin literally vanishes before you even break ground. Honestly, the only real shield you have against that kind of financial hit is an airtight, incredibly accurate pre-bid estimate. But getting that accuracy, that means getting over a massive physical hurdle.
Which brings us to part two, soil is not constant.
The absolute biggest flaw in budgeting is treating soil as a static material. It's not. It is highly dynamic. The dirt you dig out of the ground is fundamentally different in volume than the dirt sitting in the back of your haul truck, which is different again from the dirt you're eventually compacting into the site. To really nail this down, we have to look at the three primary states of soil: bank, loose, and compacted. The bank state is your natural, undisturbed earth. The loose state is what you have after excavation, when it's being hauled or sitting on a stockpile. And the compacted state is when it's been placed and engineered into a fill. Now here's the golden rule you absolutely have to remember. Water can be added or removed, and the total volume of air voids can change, but the mass of the solid soil particles? That never changes. It's only the volume that is constantly shifting across these three states.
Just look at this transition from the bank state on the left over to the loose state in the middle. When you excavate soil, you're introducing air into the mix. The total volume actually expands. In the industry, we call this swell. Then, look at the move from the loose state to the compacted state on the far right. Now you're actively driving out that air and water, compressing the material into a much tighter space than it originally occupied in the ground, and that's called shrinkage. So think about it. If your estimating software or your manual workflow isn't explicitly accounting for this swell and shrinkage, your truckload calculations and your fill requirements are going to be catastrophically wrong.
And what's wild is the sheer scale of these volume changes. Let's look at some hard data from the Wisconsin Department of Transportation. Check out the clays at the very bottom. When you move clay from its natural bank state into a loose state for hauling, it can expand by up to 58%. Seriously, imagine budgeting for, say, 1,000 dump trucks, only to realize out in the field that the soil is swelled so much you actually need almost 1,600 trucks. There goes your margin. And on the flip side, some over-consolidated clays actually have a negative shrinkage factor. That means their undisturbed natural state in the ground is actually denser than the maximum dry unit weight you can physically achieve with engineered compaction. At the end of the day, the material dictates the math. All right, part three, grid versus cross-section methods. So how do estimators actually measure all these shifting volumes in the real world? I mean, you can't just throw a giant tape measure over a mountain of dirt, right? Estimators rely on specific analytical methods to translate 2D topographic data into rock-solid volume metrics. The two heavy hitters are the grid method, sometimes called the borrow pit method, and the cross-section method. The grid method works by superimposing a square grid pattern right over a grading plan, and then it calculates the difference between the existing and proposed elevations at every single grid intersection. It's fast, and it is fantastic for relatively flat sites or open borrow pits. But if you're building a highway, or a railroad, or a canal, the grid method is virtually useless. For that kind of linear construction, estimators use the cross-section method almost exclusively.
Let's look at how the cross-section method actually plays out on the ground. Notice how the centerline stakes are driven into the earth at regular, fixed intervals. We call these stations. Well, those centerline stakes dictate exactly where your cross-sections are taken. At every single station, the estimator calculates the end area of the required cut, meaning the excavation, or the required fill, the embankment. You can clearly see those shaded vertical planes here. Those represent the cross-sectional end areas.
So, the million-dollar question: how do we get from those flat 2D vertical planes to a real three-dimensional volume? Estimators generally rely on the average end area formula. You take the area of the cross-section at Station A, average it with the area of the cross-section at Station B, and simply multiply that average by the distance between the two stakes. Pretty straightforward, right? But here's the catch. While the average end area formula is the industry standard, it actually tends to slightly overestimate volume. Most of the time, that's fine. But for extreme accuracy in highly expensive operations like, say, drilling and blasting rock cuts, estimators will upgrade to the much more complex prismoidal formula. It's all about protecting the budget.
Moving right along to Part 4, Avoiding Common Estimation Mistakes. Okay, even if you have the right formula and you totally grasp soil expansion, estimators can still fall into some very specific traps that will just obliterate a profit margin. Let's run through a quick preventative checklist. First up, topsoil stripping. You know topsoil contains organic matter, so it absolutely cannot be used in engineered fills. It has to be stripped away. But if you fail to account for that stripping in your math, you alter the existing elevations, which entirely shifts your zero line or daylight line. That's the critical boundary separating your cut and fill zones. If that line moves, your entire earthwork balance is basically trash. Second mistake, ignoring side slope requirements or those really tricky transition sections where a roadway shifts from cut to fill. Third, like we just talked about, using the standard end area formula for massive, expensive rock cuts instead of the prismoidal formula. Just don't do it. And finally, failing to account for soil subsidence. The sheer weight of your heavy earth-moving equipment alone can cause the natural ground underneath your fill to settle by several tenths of a foot. What does that mean? It means you're going to need significantly more fill material than your 2D design plan suggests just to hit your target elevation.
So, I'm going to leave you with this to think about on your next bid. Whether you're crunching these numbers by hand or running advanced digital surface modeling software, is your estimating workflow actually accounting for the living, breathing, volume-shifting nature of the soil beneath your feet? Because if you treat dirt like it's just a constant, static variable on a spreadsheet, the hidden financial risks of earthwork will absolutely catch up with you. Thank you so much for joining me for this explainer on the Info Engineer. I really hope this analytical dive into volume estimation helps you protect those margins on your next big project. Catch you next time.